Oh, good, Nuriya.
Hi everyone, welcome to the tutorial. So my name is Nuriya. I'll be doing all the tutorials in this semester. Just a quick introduction. I'm a fourth year PhD student in a Quantum Information Theory group. Yeah, I work mostly on paradoxes and quantum foundations. So what you will hear about in the second part of the course, the last part of the course. So you can always contact me by my email, which you can find on Moodle, or just post the questions on Moodle forums if you have anything to ask about lectures or tutorials. So in exercise classes, we'll basically discuss important aspects of the lectures on which the exercise sheets are based on. And these things would also help you in the lecture, and sometimes we'll just repeat some stuff which was already in the lecture, but a bit slower. So the exercise sheets will be posted on Tuesdays. Then today, on Wednesday, we discuss them, and on Friday or next Monday, the solutions are posted. You don't have to give in any solutions. Yeah, please feel free to interrupt me anytime during the tutorial. All questions are welcome. It's better to ask them now than to struggle with them later in the semester. So today I'm going to do two things. So first, you might have seen that on the Moodle there are now two exercise sheets: the 0th exercise sheet and the first exercise sheet. So the 0th exercise sheet is meant for you to refresh some notions you've learned in, for example, quantum information theory course or quantum mechanics courses to bring you to the same level. And this is just the basic things that you have to know to understand what's happening in the course. And then the first exercise sheet concerns already things that were discussed in the lecture, namely what is the temperature of the qubit, and what does it mean for the unitary to be energy preserving or non-energy preserving, given a particular Hamiltonian. So to start slow and for you to be more comfortable, I'll just start with the 0th exercise sheet and just quickly recap all the things that are there, which are Unitarian Hermitian operators. What are these operators? What are their properties that we're going to use? Then go to the notion of the trace and partial trace. Then also talk a bit about thermal states, and then I'll go on to talk about the actual content relevant for the course. So, okay, let us start with this. Please ask me questions if anything is not clear. Okay, so let's start with Unitarian Hermitian operators. So Unitarian Hermitian operators are operators which are defined as some of the space H. And we call an operator unitary U if the following holds, that U dagger U equals U dagger equals identity. So basically, what is a unitary operator? Unitary operator is defines a linear transformation. It's important to remember that conceptually, what a unitary does it maps one orthonormal basis in Hilbert space to another orthonormal basis. And every unitary can basically be defined by this transformation. So if you know the basis you're starting with and the basis you're mapping to, and you know which state goes into which state, the exact mapping, you have the unitary. Then there is a notion of a Hermitian operator. So this is over space. This is the unitary. Hermitian operator, we call A a Hermitian operator if A is equal to A dagger. And usually when we say that some, we talk about some observable and quantum mechanics, we assign to each observable an operator, and these operators that we assign to observables are Hermitian. Hermitian operators have this property that all their eigenvalues are real, which makes them perfect for describing observables. Okay. Another thing is the operator exponential. So for each operator, we can define this operator exponential, which one way to define it is via the Taylor series. So you can always describe the exponential in terms of the Taylor series. And here you just have the operator as its argument. So and the operator exponential is important in quantum mechanics because to describe the time evolution of the system, what we use is exactly the operator exponential. So if we have Hamiltonian H, the system described by Hamiltonian H, then from solving the Schrödinger equation, which you all must have seen in quantum mechanics schools, we can basically write that the time evolution then that the system undergoes can be written as u equal e to the power minus I h. So again, as Rolf said in the lecture, ideally one also needs to write here over h bar, but here we don't care about it, so we assume we work in the units where h bar equals 1. So also from the fact that h is the Hamiltonian of the system has to be a Hermitian operator, it follows that u, which is described by its potential, is always a unitary. Moreover, one can generally show that if A, so if A is Hermitian, from this it follows that u equals e to the power I A is unitary. Okay. Another property of the operator exponential is if we have the exponential of the sum of two operators A and B, then we can write it as a product of two operator exponentials if these two operators commute. these two operators don't commute, there is another specific formula for that, which is called Baker-Hausdorff formula. But this will not, you might have seen it in the quantum mechanics course, but here we will not need it. Okay, so we know that if we have this Hamiltonian, for example, or any Hermitian operator, then we can write U as operator exponential of this Hermitian operator and get a unitary. So the converse is also true. So if U is a unitary, then we can always find a Hermitian operator H such that U can be written as e to the power, here we can even add it, minus IHT. So what does that mean? So mathematically, it just means that if we have a unitary, then we can always find a Hermitian operator such that this unitary is the operator exponential of this Hermitian operator. What it means physically is that whenever we have a system and we say that it undergoes some unitary evolution, we can always find a Hamiltonian such that which implements this evolution. So for example, so for example, when you want to Einstein-Galler experiment, when you want to couple the spin of the system to the direction of the magnetic field, then you write a Hamiltonian which couples these two. Let's say to the something like this, and then this course we can always write this as the unitary, using this exponential, but you can always do the converse. So for example, if you're given some unitary, you find this Hermitian operator, then you see it couples this degree of freedom to another degree of freedom. And so for example, if you encounter a question, I have this unitary, how do I implement it in the lab? What you have to answer is, I need to find this Hamiltonian operator which does it, and that will give you the answer. Okay. So I'm not proving all these claims right now. So you either know already the proofs, or you can just refresh them and then look up the solutions to the zeros exercise sheet. Then there is another important property which concerns two operators which commute. So say we have two operators, A and B, which are Hermitian, and they also commute. And if they commute, then there exists a basis in which both of these operators, A and B, are diagonal or block diagonal. So this is an important property to remember. Basically, if you have these two operators and you see that they commute, the first thing that comes to your mind should be, I can I can simultaneously diagonalize them in the same basis. So can I go to the proof of this, or is this more or less familiar to you? Okay, yeah. But this is basically the first thing that should spring to your mind. Just bring to your mind when you see that two operators can meet. This is a very important one. Okay, then we go to the trace and partial trace. So suppose that we have an operator A. And the number space H. And we have the basis in H, which we label as J. Then we can define a trace array as sum over J, J, A, J. So basically, if you write A as a matrix, then the trace array is just the sum of its diagonal elements. The trace does not depend on the basis the operator is written in. This is also a fact from linear algebra. And the trace is also, it's linear. It's cyclic. And it's, as I said, basis independent. So by cyclic, I mean it has this property that if we have two operators, A and B, then the trace of AB equals the trace of BA. This holds for any two operators, they don't need to commute. Now, let us consider two Hilbert spaces, HA and HB. So say that A describes the quantum system A, and B describes the quantum system B. Then to describe the joint, all joint states in the systems A and B, we would need to take a bigger Hilbert space, which would be the tensor product of these two spaces. And suppose that we have a system which is described by density matrix rho AB. Now we can look at the notion which is called the partial trace, and the partial trace allows us to basically trace one system and trace out one system and look at the states and the density matrix of the other system. So, for example, if we want to trace out the second system, so we trace out the system B, and for this we need to define a basis in a Hilbert space HB, which we label as JB. Then we basically sum up in a way very similar how we summed up the terms for finding just the usual trace, but we only need to include the basis states of the system B. So basically, it's the sum over J, identity on A, J, B, rho AB, the conjugate of this expression. So one identity on A, J, B. So this is just a revision.
if you want to again remind yourself how one proves the properties of the trace and some examples of the partial trace, please look at the zero text sheet. Okay, but these are the things you should be very comfortable with in this course. So if you feel a bit shaky about them, please revise or ask me questions. Okay, now we go to something which is a bit closer to what we did today in the lecture. It's a notion of the thermal state. So suppose that we have a system which is described by the Hamiltonian. So it's sum over I, EI, II. So just so basically this Hamiltonian in this basis I is diagonal, and each state I corresponds to the energy EI. And then we say that the system is at temperature T. So for those of you who took classical mechanics, or maybe this was covered in thermodynamics, imagine just a classical system with a lot of levels, and the levels have the energy E0, E1, E2, and so on, En. And then we put that system at the temperature T. So the population distribution, so the statistical description of the system would be the so-called Boltzmann distribution. Or I think it's also called Boltzmann-Gibbs distribution. So for example, like a classical example is how the energies of gas particles are distributed depending on their velocity. Or another example is how the number of particles depends on the height, how high you are in the atmosphere. So this is all will be the probability, for example, to find a particle at the height h would be proportional to e to the power minus mgh over kBt, where h is the height. So basically, the idea here is that to write such a distribution, we just write the probability to be at the energy EI as proportional to e to the power minus EI over kBt, where kB is the Boltzmann constant and T is the temperature. And we can extend this notion to the quantum systems that we are considering. Why? Because as you remember, the density matrices which describe mixed states can be interpreted as density matrices corresponding to classical probability distributions. So for example, to describe a setting where you have a coin and it lands on heads with probability 1/2 and on tails with probability 1/2. To describe this as a quantum system, you can write it as a density matrix rho, which would be 1/2 0 0 plus 1/2 1 1. And here, the idea is basically the same. We take that classical probability distribution, this Gibbs Boltzmann distribution, and we write a density matrix. And this is this is the thermal state. Which we call tau t, which is basically e to the power minus I sorry, without an I, e to the power minus h over kBt over the partition function z. So the partition function z is here just to ensure the normalization, because in a both classical case, and so for example, in classical case, you need all the probabilities to sum up to 1, which means that you have to scale every probability with respect to some scaling factor. And here, the fact that probabilities sum up to 1 corresponds to the fact that the trace of any density matrix has to be equal to 1. So partition function just ensures that this normalization is fulfilled. Okay, so now, what's the time? Okay, very good. Okay, now let us see what this thermal state looks like when we have this type of Hamiltonian. So basically, what we have here is e to the power minus sum over I, ei, ii over kBt with the partition function. So in this case, it's very easy to calculate this operator exponential, because the operator in question is diagonal. While I'm erasing the board, you can already calculate the answer. I mean, you already see it in the lecture, so I guess it's not a secret. So tau of t equals that exponential over z. So what will be the answer? Feel free to speak. It's fine to make mistakes. Yes, so basically what it would look like is e to the power minus, so sum over I, e to the power minus ei over kBt, ii, and over the partition function. Yeah.
I have a question.
Yes.
What do we do in general if we cannot diagonalize our
The Hamiltonian can always be diagonalized.
Yeah, okay, but if we are unable to, because it's a very hard Hamiltonian. Oh, don't care about it, just say, okay, we can always apply the basis.
It's a Hermitian operator. It's diagonalizable by definition. I mean, not by definition, but it's a fact from linear algebra.
Yeah, I mean, I agree.
Yeah.
But it's really hard to diagonalize.
I mean, okay. So look, I guess then you can use some computational method to diagonalize it approximately.
Okay. So we always assume we can always find.
Yes. Yes. We assume that. Like, okay, of course, this is a theoretical consideration, and maybe sometimes it will be hard. But here, for all our purposes, we assume that this is in principle exists, so it's in principle computable in some fashion.
Do we always have a finite basis? Maybe work in a finite dimensional space.
We can have infinite dimensional spaces.
Yeah,
in principle.
In principle, but if this stores to be prohibited in any way, because because for instance, as you have written the expansion of the operator, the exponential, you cannot do it for certain operators, right?
Okay, so I think in quantum thermodynamics part, we only deal with finite dimensions. Like in a clock's part, they're going to be some infinite dimensional systems, but that's a completely different topic. So yeah. But like here, when we consider, so for example, here, if even if the system is infinite dimensional, but the number of levels is countable, so is countable, then you can still write this this distribution in such a way, right? So it's not a problem. Yes.
When you should use the thermal state,
Yes.
it's a mixed state that corresponds to specific Hamiltonian specific temperature.
Yes.
But then in the lectures, for example, we say that qubit always has some temperature. What it doesn't really mean that any mixed state of a qubit can be written as a thermal state, or does it? Or like, how does the specifics of the thermal state corresponds to an arbitrary mixed state of a qubit?
Okay. Yeah, we'll come to that later, to looking at the temperatures of a qubit. But here the idea is that here we fix both the Hamiltonian and the temperature. Whereas for the qubit, you would have fixed Hamiltonian. You would have fixed Hamiltonian, but and fixed state, but you wouldn't have a fixed temperature. Then basically, because you would have one free parameter which you could choose it and say that this is my temperature. But we will come to some examples of it. Also, basically, like here, density operator is also a Hermitian operator. So from some theorem and linear algebra, it is always diagonalizable. So basically, what that means is that if you have a state of a qubit which is mixed, you can always, or any actually state of the qubit, you can always diagonalize it. It's just in the case, for example, when the state would be pure, then the final matrix in diagonal form will have rank 1. Okay, so very good. And then the partition function, as I said, is just the normalization. So basically what we need to calculate is the trace of this matrix. And then when we divide this expression by this trace, we'll get that the trace of this whole expression will be 1. So basically, then the partition function is just the sum of these elements. So, for example, if you have qubit. So we have a two-dimensional quantum system with basis states with labels 0 and 1, which is described by the Hamiltonian, which we call delta 1, 1. So this corresponds to that Hamiltonian where the basis state 1 has energy delta and 0 has the energy 0. So graphically, we also draw this as like this energy diagram. This is state 0, this is state 1. And here we have the energy difference between delta. So this is where the direction which corresponds to energy, and this corresponds to like systems that we consider. Okay, and so for example, if we take the system and we say that we write a thermal state at the temperature T, then we would get here, so let me write 1 over Z, just normalization. And here we would get e to the power minus 0 over kt. Off diagonal elements are 0. And here we would get e to the power minus delta over kt. And this will be, of course, 1. And Z in this case is 1 plus e to the power minus delta over kt. So basically, in the end, we would just get the matrix 1 over 1 plus e to the power minus delta over kt, 1, 0, 0, e to the power minus delta over kt. And the ratio between two of these diagonal elements is exactly this Gibbs factor that Ralph was talking about in the lecture. Okay. Actually, let me even use the space here. So now let us consider two systems which are not interacting. So let's call them A and B. Non-interacting, by this I mean that their joint Hamiltonian can be written as HA tensor product identity on B plus identity on A tensor product HB. So each of the systems has an individual Hamiltonian HA and HB, and there is no interacting term between them. And each of these Hamiltonians, we write it in a form, in its diagonal form. So we write the HA as sum over I, EIA, IA, identity on B plus identity on A, tensor product sum over J, EJB, JJB. Suppose that now I want to write a thermal state on both of the systems at some temperature T. Can somebody already tell me how does this state relate to the thermal states on individual systems A and B? Yes. Why? Yeah, so because these two commute, and so we can separate the exponential, exactly. So per definition, we just write this as, this is HAB over KT over the partition function Z. Just one notation thing is that also was used in a lecture, that sometimes to have to write less and also don't write this division, we note 1 over KT as factor beta. So beta is factor which is inverse proportional to the temperature. So like in this notation, it will be e to the power minus beta HAB over the partition function on A and B. And indeed, when we write this out, we see that these two operators commute. So according to one of the properties that I listed earlier, we can just separate this exponential into a product of two exponentials. Beta 1 on A, tensor product HB. What happens with the partition function? Well, now we have to write the partition function for this joint system. Okay, one way is just to to continue calculating here and just normalize. The other way to see it already now is, so we have a joint system and we can define a basis in the system, which would be I on A, tensor product J on B for all Ij, where these are the bases and respective systems A and B. And then the eigenvalue, which will correspond to these basis elements, for the Hamiltonian would be just EI on A plus EJ on B. This is the eigenvalue. Then we can just write the partition function as the sum over Ij e to the power minus beta EIA plus EJB. Okay. Here, this exponential can be written as e to the power minus beta HA tensor product 1 on B. And the second analogously can be written as identity on A tensor product e to the power minus beta HB. And here we have the sum, which we separate into two. So it will be sum over I e to the power minus beta EIA, sum over J e to the power minus beta EJB. And then what we will get, these two will give us the thermal state on A, temperature T. These two will give us the thermal state on B at temperature T. And we will get that this is just the tensor product. Okay, of course, this is only true for the case when these two systems are independent of each other. So only when they're non-interacting, we can write the thermal state on a joint system as just a tensor product of thermal states on individual systems at the same temperature. Okay, I think now it's time for the break. So we stop for now and we meet in 1:45. Please ask any questions if you have. Okay, let's start. Okay, so now that we talked about the form of the thermal states and some of its properties, now let us turn to the temperature of the qubit, which was also discussed in the lecture. So we already seen in the example how we can write the thermal state for a qubit with the Hamiltonian delta 11 for the temperature T. What we're going to look at now is that we can find is kind of a different parameter problem. So here we would fix the temperature and write the state. Now we will write the state, fix that state, and then find to what temperature it corresponds. So basically the procedure here is the following. So we have some state of the qubit rho, which is a 2x2 density matrix. We can always diagonalize it. And then every such diagonal row can be written as a thermal state for some T. We'll use either T or we will use beta, which is the inverse of T. So again, back to our qubit with the Hamiltonian delta 11. So consider the following examples. So first, let us assume that the qubit is in a state. So it's in a pure state 0, which corresponds to the density matrix 0, 0. Now the question is, to which temperature does the state correspond? So suppose it corresponds to some temperature T or beta, then we know that the thermal state can be written as, for the qubit, as that expression we have there in the example. So we just write that instead of 1 over kT, I will write beta. So here we have 1 over 1 plus e to the power minus beta delta 0, 0, e to the power minus beta delta over 1 plus e to the power minus beta delta. Okay, so to find this beta, we just have to solve these equations. And here, what we need is that this element is equal to 1. This automatically ensures that this element is equal to 0 because these two elements sum up to 1. Okay, so this means that 1 plus e to the power minus beta delta equals 1, which means that we need e to the power minus beta delta go to 0, which is achievable when beta is plus infinity. So here beta can be seen just as a parameter. So basically, if beta is plus infinity, this means that the temperature is tending to 0, right? And just again, imagine a classical system which has two levels, 0 and 1, which are separated by this energy gap. And then assume that the system is at a temperature 0, or the temperature very close to 0. Of course, then the probability to find the system in the ground state, in the state 0 with a lower energy, will be exponentially bigger than to find it in the excited state. And if the temperature is tending to 0, then all of the particles in this classical system would be in the ground state. And here it's basically we concluded the same, right? So we looked at the system which is in the ground state, and then because the probability of finding the system in the ground state is 1, then we concluded that the temperature of the system is 0, or alternatively beta is plus infinity. Does this make sense? So this is a kind of a physical correspondence. Okay, now will be something which makes sense. Yes.
So I was wondering, does it also hold for quantum mechanical systems that an absolute temperature of 0 is unreachable?
Well, I mean, you can cool down the system until the temperature 0, like in steps. Yeah, I think it's true for. Yeah, I think it's true for all physical systems. Like as an experimental fact, yes. But I mean, here kind of we introduce this temperature as just a parameter in the problem, right? So it does not necessarily relate to the actual physical temperature in the lab. Yes.
Maybe a related question. So because temperature is usually defined on an ensemble, it's it's like a statistical variable. This Qubit system is just like a system of quantity. Should I do it, as you said, just as a parameter, or maybe another interpretation that I wrote about is that it is like a Qubit submerged in like an environment, and this environment, and it has the same temperature as the environment which has both temperature.
So this will use, I guess in some sense, yes, because this will use this thermostates as just accessible states, the states that we can always take from the thermal bath, which is at that temperature. So I guess in that sense, this analogy makes sense. So yeah. Does it make it clear?
Yeah,
or?
I guess it will make more sense for me actually.
Yeah, I mean, I guess it would, yeah, it will make more sense when we look at the thermal machines and things like this. And
I guess it's like a plausible explanation. It's just like
yes, yes, but still, still, you can see this temperature as just a mathematical parameter of this particular state. So it's just like, oh, you have a state. I can always describe it as having this Boltzmann probability distribution. Moreover, now we will see in the next example that next example will be not so clearly physical, because we will get the unusual value of temperature, so to speak. So you can already start doing the second example. The second example is, what is the temperature of the qubit if it is in the excited state? So if the system is in a pure state 1. I will not take this. So again, we need to write that this is equal to that expression. Which means that or maybe better if I write that the first is 0. So can you identify what should be the value of the beta in this case? Yes. Yes, exactly. So for this to be to hold, and we can say that this kind of tends to 0 or equal to 0. E to the power minus beta delta has to tend to infinity. This means that beta is minus infinity. So here it's, yeah, it's not so, the physical here, in this case, the physical analogy is not so clear. Not as clear as in the case of when we have the temperature equaling to 0, because here what we would have is the temperature also tending to 0, but from the negative side. So in this case, we just treat the beta as this mathematical parameter. And finally, the last example is the fully mixed state. Say mixed And the fully mixed state for the qubit can be written, as you know, as 1/2 0 0 plus 1/2 1 1. So corresponds to the density matrix 1/2 1/2, which is again we need to equal to this form. Okay, and this means that 1/1 plus e to the power minus beta delta equals 1/2. What is beta in this case? Yes. So in this case, beta equals 0. And having derived these three results, basically we can draw kind of a the beta, so the direction of the beta axis, and then we can just see to which values of beta which states correspond to. If beta is -infinity, it's 1 1. Beta is 0, it's mixed, so it's identity over 2. And if beta is +infinity, then it's 0 0. And you kind of can see that, for example, if we are moving from the 0 0 state, which is pure, towards the maximally mixed state, which has 1/2, both of which diagonal elements are 1/2, and then we move to the 1 1 state, which has only one non-zero diagonal element corresponding to 1 1. We see that, so if we, for example, move between +infinity and 0, we would have the following form. We would have something with where most of the population would be in this diagonal element corresponding to 0 0, and here would be less. There will be 2 zeros. And moving from 0 to -infinity, we would have a state with the opposite population. So we would have less population for 0 0 and more population for 1 1. So basically from this diagram, if you're given a value of beta and you know if it's less than 0 or bigger than 0, or you know how, for example, if you have like beta 1, which is less than beta 2, but are both bigger than 0, you already can tell how the populations of the ground state relate to each other for these two states. So it's just good to have this diagram in your head. Okay, are there any questions? Yes.
What's the physical meaning of having beta equals to -infinity?
Good question. So what's the physical meaning of the beta having equal to -infinity? As I said, there is no kind of clear physical meaning. If you just calculate it mathematically, you would get that t, which is the inverse of beta, also tends to 0, but from the negative side. So basically it would be the limit of t as t goes to like -0, right? And it's unphysical in some sense. It's like in classical sense for the classical physical systems at temperature T. This is not a physical situation because in physical systems, what we have is the energy levels which have higher energy have less and less population, because basically temperature T, in some sense, it's can be seen as an average energy that the particle has in this classical systems, right? And so basically then if the energy of the level is much higher than this KT characteristic energy, then it's kind of harder and harder for the particle to get there, or the particle is less I mean, in this case, what we have, for example, for this 1-1 state, we have an unusual situation that like all of the population of the system is on the excited state, which in classical systems does not happen. However, since we have introduced this parameter, which we call the temperature of the qubit, we can kind of extend mathematically this parameter beyond just being from 0 to plus infinity, but also going into the minus infinity scale. And this is physically, if you see a qubit which has a negative beta or negative temperature, this just immediately tells you that it has higher population on the excited level and not on the ground level. Okay. Any more questions? Okay. Yeah, so I advise you to keep in mind this diagram, and because this is also important for the notions of the virtual temperature and virtual qubits, which we're going to see in the next tutorial and lecture. So yeah, just make sure you're comfortable with this. And okay, one final thing I want to talk about today is energy preservation and how we calculate energy for a system with a particular Hamiltonian, and in which cases this energy is preserved under transformation. This is also very important because throughout the course, we're going to look at different operations that we can perform on the systems. And this is the class of operations we're going to be particularly interested in, the ones which preserve the energy of the system. So you can see it as an analog for the classical notion of how can I change the thermal state of the system and not pump in any additional energy. Okay. So we look at the operations on the system. And because we work in the framework of quantum theory, these operations can be described as unitaries. And now we want to see for which unitaries it holds, such that independent of the initial state of the system, the unitary preserves the energy of the system. So suppose that the system is in a state rho. Then first thing, how do we calculate the energy of the system, or the expectation value of energy? So to calculate the expectational value of any observable, as you know, we just need to take the trace of the corresponding observable multiplied by the density matrix. In this case, the energy observable is given by the Hamiltonian. because Hamiltonian is describes the energy of the system. So now what I claim is that if the unitary commutes with a Hamiltonian, then after I apply the unitary on the system, the energy of the system is preserved. Summer's energy stays the same. Okay, so what does it mean that U and H commute? It means that UH equals HU. Okay, so now let us apply our unitary. It maps the initial state of the system rho to U rho U dagger. Now let us calculate the energy in this state. So we call it E prime. This is the trace of the Hamiltonian, rho prime. This is rho prime, which is the trace of H, U, rho, U dagger. We know that H and U commute, so we can switch these two terms. So it's going to be U, H, rho, U dagger. Now we can use the cyclic property of the trace. And by this, we just put U from here to here. So this is going to be trace H, rho, U dagger, U. Since U is a unitary, this is identity. And we are left with trace of H rho, which is the initial energy of the system. Okay, which means that the average energy is preserved. Now let us look. So this is an important condition. So whenever you construct a unitary which you want to be energy preserving, you should always check if it commutes with a Hamiltonian. Okay, now let us see a couple of examples how we can construct such unitaries. So this is more about thermal state. So suppose that we have a Hamiltonian H, which is the following. So say it's a delta 1, 1 plus delta 2, 2 plus 2 delta 3, 3. So as an energy diagram, one can draw this as, so we have 0 is the energy, 0 has the energy 0, 1 and 2 both have the energy delta, and 3 has the energy 2 delta. Okay, so this is a 4-level system where these 2 levels are degenerate in the energy. So just to emphasize, this corresponds to this matrix. So suppose you see this Hamiltonian and you ask a question, please construct an example of a energy preserving unitary. So there is an intuitive way to see which unitary would be energy preserving. One thing to remember about unitaries, which I already emphasized in the beginning, is that unitary simply maps from one basis to another. So by identifying both bases and identifying mapping between them, you identify the unitary. So what operation I can do on the system which would preserve the energy?
Move 1 and 2?
Yes, exactly. Yes. So basically, in this case, we map from, we construct a unitary, which maps from this basis to the same basis. But it indeed swaps 1 and 2. And of course, one can show that indeed this unitary, which I'll write in a moment, will commute with the Hamiltonian. But also intuitively, you can see that, oh, I swap the population of 2 levels which have the same energy. So the operation should preserve the energy, because it anyway preserves the net population on levels 1 and 2. So how we write the unitary, so basically 0 is mapped to 0, plus 1 is mapped to 2, plus 2 is mapped to 1, plus 3 is mapped to 3. Okay, and as a matrix, this can be written as this. Okay. So now let's take the same Hamiltonian and see what would be the an example of non-preserving transformation, energy non-preserving transformation. While I'm wiping the board, you can already come up with 1 or 2 or several. Okay, so can somebody give me an example of, yes?
Yeah, instead of changing 1, we could change 1, 3, sorry, 0 and 3, for example.
0 and 3, okay, yes, exactly. So say 1 and 2 stay the same, and 0 goes to 3, 3 goes to 0. Exactly. So U not preserving, we write it then as 0 is mapped to 3, plus 1 is mapped to 1, plus 2 is mapped to 2, and 3 is mapped to 1. So basically, as a matrix, this would be 0, 0, 0, 1, 0, 0, 1, 1. Okay, so this is generally a unitary which does not preserve energy. However, there is a caveat. So this this condition that we formulated there, that U and H have to commute, is a necessary condition when you talk about any initial state of the system. However, even if that condition is not fulfilled, for some states of the system, the energy could be still preserved. Like, for example, in this case, like if I take any state in a subspace of the states 1 and 2, for which nothing changes, the energy of the state would be preserved. So basically, for example, or rho, which is, yeah, we can even take example 1, 1, or rho 2, 2, or any combination within the subspace, the energy is preserved. Yeah, however, in the course will be mostly depending on that condition, because we don't want to depend on the exact form of the state rho, so on the exact state of the system rho. But you should remember that there is this caveat. Okay. I think this covers all material which is in the exercise sheet 1. Yeah, next week we'll talk about virtual qubits and already some cooling protocols and virtual temperatures and so on. So please revise the notion of the temperature of the qubit and ask me any questions if you have any. Okay, yes.
I think right now the sheet 1 already has a solution on it. Upload it and solution afterwards.
Yeah, okay, I already was informed of this. Yeah, I'll upload just without the solutions, and then I'll upload the solutions later. Okay, no questions? Then thank you for your attention. See you next week.